Hi folks. Today our topic for our notes is the system of equations applications. Applications meaning we're taking what we know about systems of equations and we're applying it to real situations. A lot of times the questions that people ask in a math class is, when are we ever going to use this? When we're talking about systems of equations, this is the type of situation that you might use it for. We've got a lot of different scenarios today. Obviously, as an adult, you're not going to be creating systems and solving these systems algebraically, but the more difficult ones that we do, the more likely you are to be able to do things like solve puzzles and apply your knowledge to simpler scenarios that still involve systems of equations. So the process today, we're going to be given a word problem. The process is, first, we need to define each variable. We need to state what each variable will represent. Now, so far we've been talking about systems of equations that have two equations and they're made up with two variables. Most of the time it's been x and y. Today it's going to be a little different because we have word problems. So instead of x and y, we might have n for nickels and q for quarters, or we might have, different variables, and so we need to define them. We need to say what they are in the equation so that we can relate it back to the problem. After we define the variable, we're actually going to have to write the equations today. So we're going to have to take the information from our problem and we're going to have to create the equations that go with it using our variables that we defined. So once we write each equation, we're going to solve the system. And since we have equations, we're going to solve it algebraically. We're going to solve using substitution or elimination, whichever one you are more comfortable with or whichever one the system is set up to use. And then finally, we're going to write our answer. Typically, we write it as an ordered pair, but because we're not guaranteed to have x and y variables here, we may have something else. We need to write our answer in a way that makes sense and relates it back to our problem. So we need to write it in a complete sentence. Okay. So I'm going to scroll down, trying to keep our process in view still. There we go. We're moving on to number 1. Number 1 says, the perimeter of a rectangle is 24 meters. The width of the rectangle is 30 meters less than 5 times the length. Find the width. So I'm going to circle what it is that I'm supposed to be finding. This is an old skill, but it's still useful. I'm going to find the width. In fact, because I'm supposed to write my answer in a complete sentence, I'm going to go down to the line where it says solution. And since I'm finding the width, I'm going to go ahead and write the width is, and then that way I know what I'm finding and I can just fill in my answer. So let's define the variables. It told us that the perimeter of a rectangle was 24 meters. It talked about the width. It talked about the length, and those are both things that go into the perimeter, and so our two variables need to represent the length and the width. Typically, L represents length and W represents width. I would advise you against using just like a script, not a script, I'm sorry, just like an L like this or an L like this. Those are probably not good ideas. When you use L as a variable, it's a great idea to use the script L, the cursive L, because it doesn't look like a 1. So just handy tips as you work in your math class. So the equations come from the information in the first two sentences. The first sentence says that the perimeter of a rectangle is 24 meters. Well, in order to find perimeter, you add up 2 of the lengths and 2 of the widths, because a rectangle has 2 lengths and 2 widths. So 2 lengths plus 2 widths equals the perimeter, which is 24 meters. So there's one equation. The second equation comes from the second sentence. It says the width of the rectangle, so W, is that translates to an equal sign. 30 meters less than, so something minus 30, but that probably should go at the end of the equation. So 30 meters less than 5 times the length. So 5 times the length. So I'm going to go ahead and write my equation. The width of the rectangle is 30 meters less than 5 times the length. So there's my second equation. So I've written them. I want to solve the system using substitution or elimination. I'm going to go ahead and solve using substitution because I have a variable that's already solved for. I'm going to put this in place of W. So I have 2L plus 2 times the width, which we know from the other equation is 5L minus 30. And that should be equal to 24. If I'm solving the equation for L, I need to get rid of the parentheses, so I need to distribute my 2 with multiplication. 2L plus 10L minus 2 times 30 is 60 equals 24. I have 2L terms, so I need to add them together. 2L's plus 10L's is 12L's. When I isolate a variable L, I need to move the constant, so I need to move the minus 60 by adding 60. I have 12L equals 24 plus 60, which is 84. And then if you undo the multiplication by dividing by 12, you would see that L equals 7. Now, that's fantastic, and it's information that we need to know, but it doesn't give me my width. So in order to find my width, I need to take my 7 for length, I need to substitute it back in. So I'm going to use the second equation. Width equals 5 times the length, which is 7, minus 30. Width equals 5 times 7 is 35, minus 30. That equals 5. So here, the length is 7 meters, and the width is 5 meters. So there is problem number 1. Okay, let's move on to problem number 2. In problem number 2, it says the sum of 4 times Lisa's age and 7 times Jane's age is 169. Jane is 1 year more than twice as old as Lisa is. How old is Jane? Well, my solution will be Jane is some amount of years old. I don't know how many, but I know that she's some amount of years old. Okay. My variables. Everything is talking about the ages of these two girls. So perhaps I need a variable for Lisa's age, and I need a variable for Jane's age, because that's what's being manipulated in these sentences. So maybe we'll make L Lisa's age. And maybe we will make J Jane's age. You may notice that even though Lisa and Jane are proper names and the letters are capitalized, L and J, I didn't use a capital L and J for my variables, and that's because typically in math, capital variables are only used for formulas. So like capital A is the area, capital P is the perimeter, capital V is the volume. So typically those denote something in a formula. Lowercase l and lowercase j would be appropriate here. So I'm going to go ahead and switch my colors. Step 2, after I define my variable, is to write each equation. So the first equation says the sum, that means adding, of 4 times Lisa's age, so 4L, and plus 7 times Jane's age, so 7J, is equals 169. So there's my first equation. 4L plus 7J equals 169. It also goes on to say that Jane is 1 year more than, so plus 1 but at the end of an equation, twice as old as Lisa is. So twice L. So that sentence is that Jane is 1 year more than twice Lisa's age. If you have 1 year more than or 1 year less than, that means you add or subtract 1 at the end of your equation. So now I want to solve my system. I again have a variable that's already solved for, so I'm going to take this, I'm going to use substitution. I'm going to put it in place of J in my equation. So I have 4L plus 7 times J, which is 2L plus 1. That's supposed to equal 169. So what I'd like for you to do, because this mirrors our first example really, really well, now that we've shown that substitution, I would like for you to continue solving the problem and try to find how old Jane is. So pause your video and continue solving. So hopefully you were able to combine like terms, move the constant, divide by 18. You find out that Lisa's age is 9, however, that's not what you were asked for. So you have to substitute 9 into your second equation to learn that Jane is 19 years old. So I'm going to move this down to number 3. Number 3 says Mrs. Garcia is 1 year less than 3 times as old as her daughter. 7 years from now, she will be 4 years more than twice as old as her daughter will be then. So this is quite the mouthful. This is a jumble of words. But I am supposed to find both of their ages. So, Mrs. Garcia is blank, and her daughter is blank. Okay, we're comparing their ages, so perhaps G could represent Mrs. Garcia's age. And D could represent her daughter's age. Okay, so I need to create my equations. Mrs. Garcia is 1 year less than, but at the end, 3 times as old as her daughter. So my equation is Mrs. Garcia is 1 less than 3 times as old as her daughter. In the second equation, though, it talks about 7 years from now. So we're going to talk about 7 years from now, Mrs. Garcia will be equals. So Mrs. Garcia in 7 years from now will be 4 years more than, so plus 4 at the end, twice as old as her daughter will be then. So twice as old as not D, but how old her daughter will be in 7 years. So she will be 4 years more than, twice as old as her daughter will be in 7 years. So her daughter's age plus 7. So what I'd like for you to do now is pause your video. This is set up for substitution. So I'd like for you to try to substitute and figure out Mrs. Garcia's age and her daughter's age. Pause your video and try to solve the system. So once you substitute 3D minus 1 for Miss Garcia's age, then you can combine some like terms. You can solve for D, her daughter's age is 12, but then you have to take this age and you have to substitute it back in to find Mrs. Garcia's age. So Mrs. Garcia is 35 and her daughter is 12. So after this example, we start seeing problems that have like monetary values. Monetary is the adjective meaning for money. So we start seeing problems that have certain amounts of money. You've seen hopefully these problems before in Algebra 1 where we talk about quarters and nickels and how much and all that kind of stuff. And so we're going to bring those back today. Number 4 says that Juan has $8.40 in quarters and nickels. He has 4 times as many quarters as nickels. Find how many quarters and nickels he has. So down in my solution, in my complete sentence, Juan has a certain amount of quarters and a certain amount of nickels. So I'm going to go ahead and define my variables. So your first thought might be, oh, well, the variables are nickels and quarters. But you have to be specific. The nickels and the quarters that we want for our variables are the amount of nickels and the amount of quarters, like the actual number of those coins. So in my variables, when I define them, Q is not just going to be quarters, it's going to be the number of quarters. And N is not just going to be the nickels, it's going to be the number of nickels. Now when I write my equation, it says that Juan has $8.40 in quarters and nickels. So remember that quarters are 25 cents each and nickels are 5 cents each. So I need to pair those with the corresponding variables. 25 cents per quarter times all of those quarters that he has plus 5 cents. Ooh, I made a mistake, didn't I? Should nickels be 0.5 or 0.05 for their monetary value? They should be 0.05. What is 0.5? How much is that? That's 50 cents. I don't want 50 cents. I want 5 cents. So be careful about that. 5 cents per nickel, and that equals $8.40 for his amount of money. Now, it also goes on to say that he has 4 times as many quarters as nickels, and these are always a little confusing. If he has 4 times as many quarters, that means he has more quarters, right? That means that in order to get these two to be equal, if he has more quarters, that means that you multiply 4 by the smaller number, by the nickels. So those are always a little confusing. If he has more quarters, then that means that the other number is what you need to multiply by in order to get it to be equal to the bigger number. So I noticed that this is set up for what? Substitution or elimination? Set up for substitution. I already have a variable solved for. So 0.25 times my number of quarters, which is equal to 4 times my number of nickels, plus 0.05 times the number of nickels is supposed to equal $8.40. Now think about a quarter. If you have 4 of them, how much money do you have? You have $1 whole. So you have 1 N plus 0.05 N equals $8.40. So if I add 1 and 0.05, I have 1.05 N equals $8.40. And when I divide by 1.05, you are welcome to use a calculator. You'll get that the number of nickels must be 8. So he has 8 nickels. But you also need to know how many quarters he has. So I'm going to substitute that in for my N value. The number of quarters that he has is equal to 4 times 8. Ooh, not 48. 4 times 8. 4 times 8 is, man, Miss Belsick can't do math this afternoon. Oh, 4 times 8 is 32. hopefully this is keeping you up a little bit with me making all of these mistakes on this problem. So Juan has 32 quarters and he has 8 nickels. Okay, so I'm going to slide this down to example 5. Example 5 is another problem that has monetary values. And so I'm going to read this problem. I'm going to help you define the variables. It's a little tricky when you define the variables and when you write the equations. This is a little bit harder of a problem. So we're going to do this one together. And then example 6, I think I'm going to have you do example 6 on your own and then you can check it. So that's my plan right now. On example 5, it says, candy worth $1.05 a pound was mixed with candy worth $1.35 a pound to produce a mixture worth $1.17 a pound. How many pounds of each kind, so how many pounds of each kind, both kinds, of candy were used to make 30 pounds of the mixture? So in my solution, I need to talk about the candy that's worth $1.05 a pound and the candy that's worth $1.35 a pound. So there are a certain number of pounds of candy worth $1.05 per pound and a certain number of pounds of candy worth $1.35 per pound. So that's my solution. I just don't know what my values are yet. So my variables should be the candies, right? And there's 2 different kinds of candy. So you can name them whatever you want. I'm going to name them candy A and candy B just because that seems like it would be easy. So candy A, that variable A, it's not just that candy. It's the pounds of that candy. It's the amount of weight of that candy. So this will be the pounds. Remember, pound is abbreviated LB, so pounds is LBS. So the pounds of candy worth $1.05. And then B will be the pounds of candy worth $1.35. So this one's really tricky. So we're talking about the pounds of candy. We need to know how many pounds of candy of each kind. So when I create my equations, it says that candy worth $1.05 a pound was mixed with, so added with, candy worth $1.35 a pound, and it equaled candy worth $1.17 a pound. So we have $1.05 times that amount of pounds of candy plus $1.35 times that amount of pounds of candy. And that's got to equal $1.17 times that amount of pounds of candy, the total amount of pounds of candy. And they don't give us that information until the very end. It says that there's 30 pounds of that mixture. So this should be a 30. Excuse me. For our second equation, we know that the pounds of candy plus the pounds of the second kind of candy have to equal the total pounds of the mixture, which is 30. So this is set up for elimination. If you don't want to do elimination with these decimals in your problem, you can always solve for A or B in the second equation and you can use substitution. That's what I'm going to choose to do because I think it might turn out to be a little bit nicer looking. So I'm going to subtract B from both sides. I'm going to get a variable by itself. So this is going to get substituted for A. So I have 1.05 times A, which from my other equation is that expression, plus 1.35 times B, equals 1.17 times the full 30 pounds. So if you type that in the calculator, you're going to end up getting 35.1. Okay. If I distribute 1.05 times 30 is 31.5. Be careful because what I just wrote, 31.5, and what I wrote before, 35.1, are very similar looking, so don't confuse them. If I distribute the 1.05 to the minus b, I have minus 1.05b plus the 1.35b still equals 35.1. If I combine my like terms here, negative 1.05b's plus 1.35b's is kind of like 1.35 minus 1.05. So that's just 0.30. It's like 35 minus 5. That's like 30. So we have 31.5 plus 0.3b equals 35.1. I'm going to get rid of my constant, move it to the other side. I have 0.3b equals that difference of 35.1 minus 31.5 is 3.6. And if you divide both sides by 0.3, your b value is equal to 12. So that's the number of pounds of candy that's worth $1.35 each. But now I need to put this back in my equation to get candy A. So we have 30 minus 12, that equals 18. So there are 18 pounds of candy that's worth $1.05 a pound, and there are 12 pounds of candy worth $1.35 a pound. Okay, last problem. So our last problem today, I'll read it for you, and then I'd like for you to practice defining the variables, writing the equations, and then solving. So it says, the larger of two numbers is 7 more than twice the smaller number. If 5 times the larger number is subtracted from 12, the result is 17. Find each of the numbers. So I want you to pause your video and define the variables. Check back when you have the variables and then you can move on. So just define your variables. So if you didn't use L and S, that is perfectly fine, but your variables need to be defined as the larger number and the smaller number in the problem. So now, I want you to pause your video and create the 2 equations with your variables. When you finish creating the equations, check back and make sure that you got them right. Pause your video and write the equations. Your first equation comes from the first sentence. The larger of the 2 numbers is 7 more than twice the smaller number. The second equation comes from the second sentence. If 5 times the larger number is subtracted from 12, then the result is 17. So take a moment to pause your video, finish the problem, solve it, write your solution as a complete sentence, and check back. Your second equation only had the variable for the larger number, so you could solve for that larger number, and you could substitute it into the first equation and find the smaller number. The larger number was -1 and the smaller number was negative 4.